Angle modulation, frequency and phase modulations. Angle modulation. Angle modulation is the process by which the angle, either the frequency or phase, of the carrier signal is changed in accordance with the instantaneous amplitude of modulating or message signal. Major E. H. Armstrong developed the first successful FM radio station in 1936. In July 1939, the first regularly scheduled broadcasting of FM signals began in Alpine, New Jersey. Angle modulation is first introduced in 1931 as an alternative to AM. It is less susceptible to noise than AM, and it has improved system fidelity and has more efficient use of power. The downside is that it requires wider bandwidth and uses more complex circuits in both the transmitters and the receivers. The applications for angle modulation includes commercial radio broadcasting, TV sound transmission, two-way mobile radio, cellular radio, and lastly, microwave and satellite communications systems. Angle modulation. Angle modulation results whenever the phase angle, theta, of a sinusoidal wave is varied with respect to time. This is the expression for an angle modulated signal. M of t is equal to V sub c times the quantity of cosine omega c times t plus theta of t. M of t is the angle modulated wave. V sub c is the peak carrier amplitude in volts. Omega c is the carrier radiant frequency or angular velocity. It is equal to 2 pi times the carrier frequency f sub c, and it has the unit radian per second. Theta of t is the instantaneous phase deviation. Its unit is radians. Whenever the frequency of the carrier is varied, the phase is also varied. The opposite is also true. If the frequency of the carrier is varied directly in accordance with the modulating signal, the result is FM. If the phase of the carrier is varied directly in accordance with the modulating signal, the result is PM. Thus, FM is the indirect PM, and direct PM is the indirect FM. As you may have already known, there are two types of angle modulation. First is the direct FM. Direct FM is the varying of the frequency of a constant amplitude carrier that is directly proportional to the amplitude of the modulating signal, at a rate equal to the frequency of the modulating signal. The second type of angle modulation is the direct PM. PM is varying the phase of a constant amplitude carrier that is directly proportional to the amplitude of the modulating signal, at a rate also equal to the frequency of the modulating signal. Angle modulated wave. The image below might look like a sine wave oriented vertically, but it isn't. It is actually an angle modulated wave in the frequency domain. Notice that the x-axis is in frequency, not in time. In the upper part of our graph, we have negative delta f and positive delta f. Both of these are the frequency deviation from our center carrier frequency, which is f sub c. So negative delta f occurs during the maximum negative modulating voltage. And during this deviation, the frequency is equal to the center carrier frequency f sub c minus the frequency deviation delta f. Likewise, for the positive maximum modulating voltage, positive V sub m, the deviation will be our center carrier frequency plus delta f. This means that the maximum deviation from the center carrier frequency is delta f. The direction at which the deviation will occur will depend upon the polarity of the modulating signal. The frequency deviation is also directly proportional with the magnitude of the modulating signal. Lastly, the rate at which the frequency changes are occurring is equal to the frequency of the modulating signal. Now this is the angle modulated wave in the time domain. The shift in phase of the original carrier signal will depend upon the magnitude and polarity of the modulating signal. As you can see in the image, the sine wave in the center is our original carrier signal. And the left sine wave is the sine wave that shifted negative delta theta, which is called the phase deviation. And the sine wave at the right side is the positive phase deviation. The phase deviation is the relative angular displacement or shift of the carrier phase in radians with respect to the reference phase. Lastly, the change in the carrier's phase produces a corresponding change in its frequency. Now, this is an angular modulated wave that is also in the time domain, but with its frequency changing with time. The minimum period T sub min corresponds to the maximum frequency F sub max, and the maximum period T sub max corresponds to the minimum frequency F sub min. Frequency changing with time. The peak-to-peak frequency deviation is determined by simply measuring the difference between the maximum and minimum frequencies. For the peak-to-peak frequency deviation, we have this formula. Delta F sub P dash P is equal to 1 over T sub min minus 1 over T sub max. The 1 over T sub min and 1 over T sub max expression is taken from the fact that frequency and time are inversely proportional with each other. Mathematical analysis. The difference between FM and PM is more easily understood by defining the following terms: instantaneous phase deviation, instantaneous phase, instantaneous frequency deviation, and instantaneous frequency. Instantaneous phase deviation. The instantaneous phase deviation is the instantaneous change in the phase of the carrier at a given instant of time. It indicates how much the phase of the carrier is changing with respect to its reference phase. Instantaneous phase deviation is equal to theta of t, and its unit is in radians. Instantaneous phase. Instantaneous phase is the precise phase of the carrier at a given instant of time. Instantaneous phase is mathematically equal to omega sub c of t plus theta of t. It also has the unit of radian, wherein omega sub c of t is the carrier reference phase in the unit of radians, and f sub c has the carrier frequency hertz. Theta of t is the instantaneous phase deviation. Instantaneous frequency deviation. Instantaneous frequency deviation is the instantaneous change in frequency of the carrier and is defined as the first derivative of the instantaneous phase deviation. So instantaneous frequency deviation is equivalent to theta prime of t, and it has the unit of radians per second. Or if we expand this, we have theta prime of t in radian per second divided by 2 pi in radians per cycle. So it is easily converted to hertz. Lastly, we have the instantaneous frequency. This is the precise frequency of the carrier at a given instant of time. So we have omega sub I of t is equal to d over dt of omega sub c of t plus theta of t. If we express that in frequency, f sub I of t is equal to f sub c plus theta prime of t divided by 2 pi. The first equation has the unit of radians and the second has the unit of hertz. Deviation sensitivity. The formula for phase modulation is theta of t equals k v sub m of t. It has the unit of radians. And for frequency modulation, theta prime of t is equal to k sub 1 times Vm of t and has the unit of radian per second. Note that k and k1 are the output versus input transfer functions for the modulators, which give relationship between what output parameter changes in respect to specified changes in the input signal. The deviation sensitivity for phase modulation is abbreviated by k, and it is equal to delta theta divided by delta v. Delta theta is the phase modulation of the modulated signal, and delta v is the input voltage deviation of the modulating signal. K has a unit of radian per volt. For frequency modulation, deviation sensitivity is abbreviated k sub 1, and it is equal to delta omega divided by delta v. Delta omega is the deviation of the angular frequency, and delta v is the deviation of the input modulating voltage. K sub 1 has the unit of radian per volt second. These are the equations for phase and frequency modulated carriers. As you can see in the left-hand side of the table, we have the type of modulation. And then next is the modulating signal. So the modulating signal can be as simple as V sub m of t, or it can be V sub m cosine omega m of t. The angle modulated wave that will be generated depending on the modulating signal and the type of modulation is shown in the last column. You will do well to have these memorized. FM and PM waveforms. This image shows the difference between FM and PM waveforms. The first signal is our carrier signal. It has a constant amplitude and constant frequency. Next, we have our modulating signal. It's a simple sine wave, also constant amplitude, constant frequency, but it has a significantly lower frequency than the carrier. The third waveform is our FM signal, and our last waveform is our PM signal. Let's start in the leftmost side. As you can see, there is a carrier signal, but no modulating signal yet. So FM and PM will result in both their rest frequencies. So these are the unmodulated signal. And then when the modulating signal started, it starts from 0 going to the positive. FM and PM starts to look different. Upon reaching the positive most peak of our modulating signal, maximum deviation occurs in FM. And so, the frequency is at minimum. It will depend upon the system if the maximum of the modulating signal is the minimum frequency for FM, or if it is the maximum frequency for FM. During this maximum deviation for FM, phase modulation, or PM, is at rest frequency. Rest frequency also equals the carrier frequency. And then when the modulating signal crosses the 0 volt range, FM would then be at rest frequency and PM would be at maximum deviation. So at maximum deviation, as you can see, PM has the lowest frequency in its entirety. And then during, again, the negative most voltage for our modulating signal, FM is at maximum deviation, so it's at the highest frequency. Again, it might be different for another system of FM. It might be the negative most part of the modulating signal will result in the lowest frequency for FM modulation. But in the case of this example, the negative most part of our modulating signal has the highest frequency for FM. And then if we look below for the PM, PM is at rest frequency for this maximum negative value. And then it will again cross the zero crossing. So FM would get back to the rest frequency, also equal to the carrier frequency, but PM will be the one at its maximum deviation. If you look closely, it has the highest frequency in its waveform. So this pattern repeats for the entirety of the modulating signal. In summary, with FM, maximum frequency deviation occurs during the maximum positive and negative peaks of the modulating signal. With phase modulation, the maximum frequency deviation occurs during the zero crossings of the modulating signal. For both frequency and phase modulation, the rate at which the frequency changes occurs equal to the modulating signal frequency. Phase deviation and modulation index. This is the phase or frequency modulated equation. M of t equals V sub c cosine the quantity of omega sub c times t plus m cosine of omega sub m times t. M cosine omega sub m of t is also equal to our theta t. This is the instantaneous phase deviation. The m is our peak phase deviation or modulation index in radians. The primary difference of PM and FM is the way the modulation index is defined. For PM, the modulation index is proportional to the amplitude of the modulating signal and independent of its frequency. Modulation index for phase modulation. We have this equation, m equals k times v sub m, and the unit is in radians. M is the modulation index and peak phase deviation, delta theta. K is the deviation sensitivity. It has the unit of radians per volt for PM. And V sub m is the peak modulating signal amplitude in volts. Take note, this is the peak modulating signal, not the carrier peak signal. For PM, the modulation index is proportional to the amplitude of the modulation signal and independent of its frequency. Phase modulation equations. As you can see, these are just variations of the same equation, wherein the previous equation was applied to substitute m with delta theta or k times v sub m. Modulation index for FM. We have the equation m is equal to k sub 1 times v sub m divided by omega sub m, wherein m is our modulation index. This is a unitless quantity, no longer in radian for FM. K sub 1 is the deviation sensitivity. It has the unit of radian per volt second for FM, and V sub m is our peak modulating signal amplitude in volts, and omega sub m is our radian frequency given in rad per second. For FM carrier, the modulation index is directly proportional to the amplitude of the modulating signal and inversely proportional to the frequency of the modulating signal. As we can see, voltage is in the numerator and our radian frequency is in the denominator. We can also substitute omega sub c for f sub m, which is the cyclic frequency in hertz or cycles per second. Frequency deviation and percent modulation. Frequency deviation. Frequency deviation is the change in frequency that occurs in the carrier when it is acted on by modulating signal frequency. It is typically given as peak frequency shift, or our delta F. This is also our frequency deviation. So it's just the same thing. This is given in hertz. The peak-to-peak frequency deviation, 2 delta F, is also called carrier swing. For FM, the deviation sensitivity is often given in hertz per volt as opposed to radian per volt second. So we have these equations. Our delta F, or our frequency deviation, is equal to K sub 1 times V sub M. And our M, modulation index, is equal to delta F divided by frequency of our modulating signal, F sub M. This is a unitless quantity for FM, as we have discussed before. Frequency deviation and percent modulation. With PM, both the modulation index and the peak phase deviation are directly proportional to the amplitude of the modulating signal and unaffected by its frequency. With FM, both the modulation index and the frequency deviations are directly proportional to the amplitude of the modulating signal, but the difference is that the modulation index is inversely proportional to its frequency. These are the equations for frequency modulation. As you can see, we're just substituting variables for our M. So these are just rearranging the same equations. Percent modulation. With angle modulation, percent modulation is simply the ratio of the frequency deviation actually produced to the maximum frequency deviation allowed by law stated in percent form. The equation is percent modulation equals delta F actual over delta F max. Note, maximum frequency deviation for a commercial FM broadcast is plus minus 75 kilohertz. So in actual commercial broadcast, the FM deviation can vary as much as 75 kilohertz from its center carrier frequency. PM and FM modulators and demodulators. Phase modulator. Phase modulator is a circuit in which the carrier is varied in such a way that its instantaneous phase is proportional to the modulating signal. The unmodulated carrier is single frequency sinusoid and is commonly called rest frequency. Frequency modulator or frequency deviator. These are circuits in which the carrier is varied in such a way that its instantaneous phase is proportional to the integral of the modulating frequency. If the modulating signal is differentiated prior to being applied to the modulator, the instantaneous phase deviation is proportional to the integral of V of t. These are PM and FM modulators and demodulators. PM and FM circuits are actually related to each other. There are just some variations in the modulators and demodulators of each. For PM modulator, it has a differentiator followed by an FM modulator. For PM demodulator, it is an FM demodulator followed by an integrator. And then for FM modulator, we have an integrator followed by a PM modulator. And lastly, for FM demodulator, we have a PM demodulator followed by a differentiator. Bandwidth requirements for angle modulated wave. Bandwidth requirements for angle modulated wave. In 1922, John Renshaw Carson mathematically proved that for a given modulating signal frequency, a frequency modulated wave cannot be accommodated in a narrower bandwidth than an amplitude modulated wave. With angle modulation, multiple sets of sidebands are produced, and consequently, the bandwidth can be significantly wider than that of an AM wave with the same modulating signal. Angle modulated waveforms are generally classified as number 1, low index, modulation index of less than 1. Number 2, medium index. That is where the modulation index is between 1 to 10. And lastly, we have number 3, high index. It is where the modulation index is greater than 10. For low index modulation, the frequency spectrum resembles double sideband AM, and the minimum bandwidth is given by this equation. Bandwidth is equal to 2 times the modulating frequency. This is in hertz. Of course, bandwidth is always in hertz. For high index modulation, the minimum bandwidth is given by this equation. B is equal to 2 times the frequency deviation. Lastly, in an unpublished memorandum dated August 28, 1939, Carson established a general rule. This is known as Carson's rule. The rule is used to estimate the bandwidth for all angle modulated systems, regardless of the modulation index. The equation is bandwidth is equal to 2 times the quantity of frequency deviation plus the modulating frequency. Carson's rule. Carson's rule is an approximation and gives transmission bandwidths that are slightly narrower than the bandwidth determined using the Bessel table and the equation for the actual bandwidth. This defines a bandwidth that includes approximately 98% of the total power of the modulated wave. The actual bandwidth necessary is a function of the modulating signal waveform and the quality of the transmission desired. Deviation ratio. Deviation ratio is the worst-case modulation index. It is equal to the maximum peak frequency deviation divided by the maximum modulating signal frequency. The worst-case modulation index produces the widest output frequency spectrum. This is the equation for the deviation ratio. dr equals delta f sub max divided by f sub m maximum, wherein dr is the deviation ratio, a unitless quantity. Delta f sub max is the maximum peak frequency deviation in hertz, and f sub m max is the maximum modulating signal frequency, also in hertz. Note, for FM broadcast band, the maximum frequency deviation is 75 kHz, as we have stated before, and the maximum modulating signal is 15 kHz. Average power of an angle modulated wave. Average power. Unlike in AM, the total power in an angle modulated wave is equal to the unmodulated carrier. Example, the sidebands do not add power to the composite modulated signal. The power that was originally in the unmodulated carrier is redistributed among the carrier and its sidebands. The average power of an angle modulated wave is independent of the modulating signal, the modulation index, and the frequency deviation. This is the formula for average power in the unmodulated carrier and the total instantaneous power in the angle modulated carriers. So we have P sub C equals V sub C squared divided by 2R, and P sub T is equal to M of T squared divided by R, or V sub C squared divided by 2R. Note that the signal power does not change with modulation, and neither does the voltage. So the average power of the modulated carrier is equal to the average power of the unmodulated carrier. The variables in the equations are P sub C is the carrier power in watts, V sub C is the peak unmodulated carrier voltage in watts. Oh wait, this is supposed to be in volts. V sub C is peak unmodulated carrier voltage in volts. R is the load resistance in ohms, and P sub D is the total instantaneous power in an angle modulated wave. So P sub C is just equal to P sub D. The average power of the unmodulated carrier is equal to the average power of the unmodulated carrier. The modulated carrier power is the sum of the powers of the carrier and the side frequency components. So we have P sub D is equal to P sub 1 plus P sub 2 plus P sub 3 and so on. So we can just substitute P1 with V sub C squared divided by 2R and P2 with 2 times V sub 1, which is the second carrier voltage, squared divided by 2R and so on. Comparison of angle modulations. FM versus PM. With PM, the modulation index is directly proportional to the amplitude of the modulating signal and independent of its frequency. With FM, the modulation index is directly proportional to the amplitude of the modulating signal, but it is inversely proportional to its frequency. Considering FM as a form of phase modulation, the larger the frequency deviation, the larger the phase deviation. If, in case an FM transmission are received on a PM receiver, the bass frequencies would have considerably more phase deviation than a PM modulator would have given them. This is because the output voltage from a PM demodulator is proportional to the phase deviation. The signal appears excessively bass boosted. PM demodulated by an FM receiver produces an information signal in which the higher frequency modulating signals are boosted instead. Advantages of FM or PM over AM. First is we have noise immunity. Most noise results in unwanted amplitude variations in the modulated wave. This is the AM noise. Angle modulation receivers include limiters that remove most of the AM noise from the received signals before final demodulation. A limiter is a circuit that produces a constant amplitude output for all input signals above a prescribed minimum input level, which is often called the threshold, quieting, or capture level. Noise performance and S over N ratio. With the use of limiters, angle demodulators can reduce the noise level and improve the signal-to-noise ratio during the demodulation process. This is called FM thresholding. With AM, once noise has contaminated the signal, it cannot be removed. Capture effect. Capture effect allows the receiver to differentiate between two signals received with the same frequency, providing one signal at least twice as high in amplitude as the other. The receiver will capture the stronger signal and eliminate the other weaker signal. With AM, if two signals with the same frequency are received, both will be demodulated and can be heard. So there will be interference between the two signals of the same frequency for AM. The last advantage is power utilization and efficiency. With AM transmission, most of the transmitted power is contained in the carrier, while information is contained in the much lower power sidebands. With angle modulation, the total power remains constant regardless if modulation is present or not. Now, these are the disadvantages of FM and PM over AM. First is the bandwidth. Of course, high-quality angle modulation produces many side frequencies, thus necessitating a much wider bandwidth than is necessary for AM transmission. For high-quality transmission, FM and PM require much more bandwidth than AM. Next disadvantage is
the circuit complexity and cost. PM and FM modulators, demodulators, transmitters, and receivers are more complex to design and build than their AM counterparts. More complex most often meant more expensive. And that's it.